the calculus of functions of several variables, and the calculus concept is limit. And so we realize that by going up a dimension, we've now introduced all kinds of different ways to talk about approaching a point in the plane. We can approach it all kinds of different ways, all kinds of different paths. And so it really kind of helped motivate this epsilon delta definition. And so we talked about this yesterday. Here's the picture to keep in mind, and we did work through an example. But the consequence of having this epsilon delta definition is it's got the same sort of backbone to limit like the first epsilon delta definition you encountered back at the beginning of your calculus class. And that means that all of the limit properties you're used to, the constant, multiple rule, sum and difference, product rule, all of these rules carry over into Calc 3 because it's using the same sort of arithmetic that the limits did in Calc 1. All right. So the long and short of all this arithmetic, all these limit laws, is basically limits respect function arithmetic as long as you're not trying to divide by 0, as long as you're not getting negatives under radicals. And so if you're asked to evaluate a limit like this, the limit as xy approaches 0, 2, you can think through it this way. X is going to 0, y is going to 2, so 3 times y is getting close to 3 times 2. 2 times 0, or x is going to 0, so 2x is getting close to 2 times 0. X squared is getting close to 0 squared. Y squared is getting close to 2 squared. And since all of this makes arithmetic sense, right, we're not trying to divide by 0, we don't have any negatives under that radical, we can go ahead and just simplify. 6 times the cosine of 0 is 1 over the square root of 4. So 6 over 2 is 3. So the substitution principle is in full effect here. Okay. And once again, that's usually what you do. If you're encountering a limit, the first thing you try is substitution. In other words, you're checking to see if the function's continuous. And if you can get away with that, then that's your limit. If direct substitution fails and you get an indeterminate form, like a 0 over 0, for instance, then you can do the same kind of things you did in Calc 1 to help resolve that indeterminate form. And so we have the same type of theorem we had in Calc 1 or AP Calc. If two functions are the same, except possibly at the point of contention itself, and you can take the limit of one and you get an answer, then that's going to be the same as the limit of the other one. So in other words, if you can simplify somehow what's going on inside the limit for all points near the target point, then you can take the limit that way. So for example here, on this limit, if you tried your direct substitution, you plug in x as 2 and y as negative 1, you would get 2 squared 4 minus 4 times 1 over 2 plus negative 2. So you get a 0 over 0 there. And so the factor theorem kicks in and says, okay, well, if you get a 0 over 0, there's a common factor creating that 0, since we've got polynomials on the numerator and denominator. And sure enough, you can go ahead and factor the numerator. Does anyone see how the numerator would factor? Does anyone recognize that form? Yep, good. It's x. Yep, that's your difference of squares. X minus 2y times x plus 2y. Whoops. Well done on that. And so we can see here that we've got a common factor. This is the factor causing the 0 in the numerator and the factor in the denominator causing the 0. And now that I've gotten rid of that 0 factor in the denominator, I can just substitute in x is 2, y is negative 1, and I get my final answer of 4. So factor and cancel alive and well. Number 2, once again, if you substitute, xy is going to the point -2, -2. So if you tried your direct substitution, you get the square root of -2 times -2, positive 4, minus 2 over 4 minus 4. By golly, we get another 0 over 0. Does anyone remember the strategy here that handles square roots? What's one thing we can do to get that to resolve itself? So we can make use of the conjugate here. Yep, very good. And basically the conjugate is just sort of completing that difference of squares formula. So you can kind of think of it that way. So you multiply here. The first terms are going to give you the xy. The middle terms, you're going to get, middle terms. So you're going to get a plus 2 root xy and a minus 2xy. They cancel out. The last terms gives you the minus 4. And I didn't leave much room for my denominator here, so I'll just put here. In the denominator, we're just going to leave things factored out because we want to cancel the factor. That's the whole point. So sure enough, got a common factor we can cancel. And now what's left over we can now substitute in. And get 1/4. Okay? So once again, multiplying by conjugates. Factor cancel, multiply by conjugates. And then number 3 here. Once again, I'll leave it to you. Direct substitution is going to give you a 0 in the numerator, a 0 in the denominator. So here we have to clear out these complex fractions. So the way I like to do it is I just multiply numerator and denominator by the least common denominator of all the little fractions. This would be the limit as xy goes to -1, 3. And now we take both of these factors and distribute them to each term. So in the first term here, the x plus y cancels out, and I'm left with a 2. Minus, on the second factor, the 2 cancels out. I'm left with the quantity x plus y. So once again, be mindful of the parentheses. And in the denominator, I've got the x plus y minus 2 times x plus y times 2. And once again, we don't want to multiply out the denominator here because we want to factor, we want to be able to cancel out this quantity. And so we almost have that up here. We just have the exact opposite of that. So we could factor out a -1 from the numerator. To get x plus y minus 2, and now we're all set to cancel that out. And now we can just substitute in what we've got here. We got a -1 over x plus y times 2. And that gives us a -1/4. Right? So all the standard sorts of algebra stuff that you used in Calculus 1 or AP Calculus to simplify these limits is alive and well in Calculus 3. Any questions on any of these examples here? Does the algebra stuff look familiar to you? Now here's something that kind of works for us. This was the limit we actually, so this was a limit where we tested it along a couple routes and we got 0 for those routes, but it wasn't enough to actually prove the limit was 0. So we had to resort to using the definition. So this is the one we did the epsilonics on yesterday. However, if you're approaching the origin, another thing you can use is polar coordinates. So if you remember polar coordinates, the way that works, and we'll be revisiting polar coordinates here in the next chapter. So polar coordinates, x is r cosine theta, y is r sine theta. And so that just comes from unit circle stuff. Okay. Then in polar coordinates, if you're heading into the origin, so xy going to 0, 0 is the same as the r going to 0. And so this is another way for us to look at limits getting into the origin. And what's nice about this is it takes away the two variables and replaces it with just the one variable with a little caveat. So we have to be a little careful on it. But let's see what happens if we look at this limit when we substitute these expressions in for x and y. So the limit as xy goes to 0, 0 of 2y cubed over x squared plus y squared. If we convert this over to polar, y is r sine of theta and I guess something we'll note here. What's x squared plus y squared in polar? So if we're going on the unit circle, well, actually, it's circular radius r. Yeah, that's just going to be r squared. All right, so this is a circular radius r. So this works out to be r squared. Now, if you remembered that, great. If not, you could go through the Pythagorean magic. But the point is, you can kind of see how this limit cleans up for us, because the factor that's causing the 0 in the denominator is going to completely cancel out. So this would be the limit as r goes to 0 of 2r sine cubed theta. And this is where we have to make a little caveat, right? No matter what angle we pick for theta, sine theta, this is continuous. This always exists as a real number. All right, so it never gets undefined, regardless of what theta we have. All right, so we can go ahead and treat this as if it were a constant compared to r. And so we can now use substitution on the r. So we'd have 2 times 0 times sine cubed theta, which would be 0. Now, where you have to be careful with this kind of thing is, let's say this popped up in your limit, and you had 2r, I don't know, tangent of theta. All right? Then tangent of theta is going to mess up at any of these pi over 2's. You follow? So we could not conclude that the limit is 0 unless we specify x is not, we're not on the y-axis. I'm sorry, not x, but theta. So the limit would be coming into 0 here, but on the y-axis, it doesn't exist. So that's where you have to be a little careful. But as long as you get something that's always going to be defined, then you're good to go. All right? And there's something on the next It's either the next test or take home, I forget which one, where you get to use polar coordinates. So this is a helpful way to show that a limit exists if you have a 0 over 0 as you're heading into the origin, and you suspect it's going to be 0. There is no version of L'Hopital's rule that works here. You could use L'Hopital if you restricted it somehow. Like if you got it into terms of limit of just R or something like that. But in general, there's no like two-dimensional version of L'Hopital's rule. And we'll talk about that when we get to local linearity next week. However, we do have the squeeze theorem, though. So the squeeze theorem, if you remember back to Calc 1 or AP Calc, the squeeze theorem was this kind of scenario. You're looking at two functions. You got a function coming up below. That's like usually your y equal g of x. You got a function coming from above. That's like your y equal h of x. And then you got the function you're interested in between all the time. So if you've got a situation where your g of x is less than or equal to your f of x, which is less than or equal to your h of x, in some open interval around a, and you've got the limit of h of x and the limit of g of x going to the same place, namely L, then the function f of x gets squeezed to go to the same limit as h and g did. All right, so that gets squeezed into L. All right, so that was your squeeze theorem. And the same thing happens in two dimensions. Only in two dimensions, you'd be looking at sort of surfaces. So you'd have this surface g of x, and you'd have this surface this would be like your z equals h of xy, and then your surface z is g of xy, and then you'd have your surface f of xy somehow coming in. You can have the surfaces kind of squeezed together too. So you can think of it as like making a sandwich and pressing the sandwich down. So once again, if you think back to previous calculus, the squeeze theorem is really built for functions where you have one factor. You've got one factor going to 0, and the other factor is bounded. All right. So for example, if we look at what's happening in this limit, we've got the limit as xy approaches 1, 0 of y cosine of y over x, like so. Excuse me, x over y. So as xy goes to 1, 0, you've got this factor, y, going to 0. And this factor is going to the cosine of 1 over 0. And if we look at, what that's doing on its own, you might remember this is one of these classic examples from Calc 1. If you look at y, or if you look at cosine, we'll do 1 over x just to see. But as you get into 0, this is going to oscillate infinitely often. Because what's happening here is that the argument of the cosine, depending on which direction you're coming into 0, is either going to infinity or minus infinity. And we know what cosine likes to do. It does this forever. So the cosine of 1 over 0 is trying to take all of these infinite oscillations and push them near 0. So this just straight up limit just does not exist. So this is infinite oscillation. This straight up doesn't exist. So you can't use the limit laws here. You can't say, well, this is going to 0. This doesn't exist. 0 times anything is 0. That's an inaccurate application of the limit properties. However, that being said, we know that cosine, no matter what cosine is, it is going to be trapped between -1 and 1. And so here's how we set up the squeeze theorem. We know that the cosine of x over y is always going to be between 1 and -1. We can think of y as being, think of this y now as being sort of the amplitude of this. Now it's tempting to just multiply through this inequality by y to get this. But what could happen, y is coming into 0, so y could be coming into 0 from the right, in which case it's a positive, or it could be coming in from the left, in which case it's negative. If you're coming in from the right, then this is perfectly fine. We don't have to worry about reversing the inequalities. But if we're coming in from the left and we multiply by y, we would have to reverse the inequalities. So oftentimes what you'll see is they'll just combine these two and they'll just do this. Right? So these two inequalities can be combined into that inequality, just looking at the absolute value of y. And I know what happens to each of these. These values on the end are going to go to 0. So I know that the limit as xy goes to 1, 0 of negative absolute value y. I can just use the substitution rule on that. And I know that the limit as xy goes to 1, 0 of absolute value y is 0. So by the squeeze theorem, the limit of what's in between must also go to 0. Okay. So once again, this is the exact same concept we had in Calc 1 or AP Calc. It carries over into Calc 3 because all the epsilonics in the definition are essentially the same. It's the same idea. Any question on the squeeze theorem here? So once again, if we want to, did I close Desmos? I think I did. Just to kind of show you a one-dimensional version of what was happening here in case you haven't seen it before. If I look at so I guess we would use x here. X cosine 1 over x. And then absolute x and negative absolute x. And we'll try, let's keep things consistent here. I think I called the actual function I used was black. The function on top was red, and then there's green. So if we zoom in here near 0, do you see how this function is getting squeezed between the two absolute values? And I don't want to taunt GeoGebra today. I mean, we could try it. All right, let's see how it handles it. GeoGebra has been very delicate the past couple days for some reason. So here we go. You can see all kinds of craziness. Let's see if we can see the squeeze here. I guess you can kind of see it. You see the squeeze happening? So, maybe if you're at home and you have less programs running, it would be a little smoother for you to look at. All right. I'm taking my computer in on Thursday because they said there's stuff that's out of date on it. So hopefully they'll get it all square, plumb, and level for us. Okay, so that's squeeze theorem. All right, continuity. You remember the concept of continuity. We had this back in vector valued functions as well. If you think of the limit as what you expect f of a to be because of sampling the function near a, and you think of f of a as what you actually get for f of a, then continuity is you get what you expect. And these are exactly the kind of places where you can use the substitution rule. You follow? And once again, that kind of broke into this checklist. People like the checklists. So for a function to be continuous, the function value has to exist. The limit has to exist. And the limit and the function value have to agree. So that's kind of what we're doing there. And then you could even do more of a checklist. You have to look at the limit from the right and the left. They all have to agree as well. All right. So how do we generalize this concept to functions of several variables? Well, we still want to have you get what you expect. So in this particular case, we're going to generalize from an f of x to an f of xy. We're going to generalize x going to a to the pair xy going to ab. And so this is once again what we expect the f of ab to equal. And then to be continuous, what should it equal? So what would go here on the right-hand side? F of AB. There you go. Okay. And once again, I encourage you to look back when we talked about continuity of functions of several variables. We had the limit as t approaches a of r of t is r of a. But in all of these situations, it's the exact same concept. Continuity means the limit equals the function value. You get what you expect to get. The behavior near the point matches the behavior at the point. And the cat agrees with that. So once again, because the limit laws work the same way as they did earlier on in calculus, and continuity is defined in the same way, combinations of continuous functions are going to be continuous, and for the most part, functions are continuous on their domains. But instead of having intervals of continuity like we did in Calc 1, we're going to have regions of continuity if we're in the plane. So for example, if you want the region f of xy here, square root of xy, we want the regions of continuity, we would just kind of look for the domain. So if I want this to be defined, whatever goes into that square root has to be positive or 0 to make sense. There can't be any negatives under there. So that would mean x times y is bigger than or equal to 0. And so we have to think, where is x times y bigger than or equal to 0? And there's a couple different ways we could, think about this. But let's just think of two numbers. We want to have two numbers that are bigger than 0. So if you multiply two numbers together that are bigger than 0, both those numbers have to be what? So if x times y is going to be a positive number, x and y have to be what? Or what are the options? Both positive or both negative. Yep. Now, since we're including 0 into that, one could be positive or one could be negative. So, or excuse me, one could be 0 rather. Excuse me, one could be 0. So we could have y equals 0 would be here. That would be the x-axis. X equals 0, this part of it. So that's the 0 case. If I could sketch it better. And then the x and y both positive is quadrant 1. X and y both negative is quadrant 3. With the understanding that if I'm approaching one of these points, say here in quadrant 3, that we're not going to be approaching it from this quadrant. You follow? So if you remember back to calculus when you had like one-sided continuity, say for the square root function, we have the same kind of thing here. If we're looking at one of these points on the axes, we're going to assume that we're taking paths in the quadrants where the function's defined. All right. So that's regions of continuity. All right. So how would we extend the definition to 3 variables? All right. So now let's see if we can go from 2 to 3. So let's just go through here. One dimension. Limit as x approaches a, f of x equals L. Given epsilon greater than 0, there is a delta greater than 0, so that if 0 is less than the absolute value of x minus a is less than delta, and the absolute value of f of x minus L is less than epsilon. So once again, this represents the distance between inputs. This represents the distance between outputs. So this is your definition from Calc 1 or AP Calc, wherever you saw it. There's your one-dimensional epsilon delta definition. Yesterday, we generalized this to 2 dimensions. So what does it mean to say the limit of a function of 2 variables as xy approaches ab is equal to some number L? It starts off the same way. Given epsilon greater than 0, there is a delta. Given epsilon greater than 0, there is a delta. So that if the distance between inputs is small enough, how small? Less than delta. Here, the distance between inputs is the distance between these points in the plane. So this is how we do the distance between inputs. Between inputs. Then we want to know about the distance between outputs. So functions of several variables, the outputs are just real numbers. So we can measure the distance between the outputs as we did here. Because f of x, y's are all real numbers. And so once again, this is the distance between outputs. Okay. So if we want to generalize this to a function of 3 variables, all we need to do is generalize this to 3 variables. All right. And one of the early themes we talked about when we first started looking at 3 dimensions is going from 1 to 2 is typically the big jump. Going from 2 to 3, we just tack on a what? We tack on a z. Perfect. So if this is going to some point in space ABC of capital F of x, y, z, and once again, that's just convention. They often will use lowercase letters for function of 2 variables and uppercase letters for function of 3 variables. This is L means. Well, guess what? We're going to start off the same. Given epsilon greater than 0, there is a delta. Given epsilon greater than 0, there is a delta, so that if, and now we need a statement about the distance between inputs. So what we talked about yesterday, we used the distance between inputs in the plane. Here, we're looking at the distance between inputs in 3 space. So how does the distance work in 3 space? We got the difference in x's, the difference in y's. We just tack on the difference in z's. So we just tack on the z there. So if the inputs are within delta units of ABC, then I look at the outputs. Once again, the outputs of a function of 3 variables is still a real number. Those real numbers have to be within epsilon of the target limit real number. So this has to be less than epsilon. So once again, this is the inputs, distance between inputs, distance between outputs. And one of the things I really want you to get out of Calc 3 and appreciate in Calc 3 is that it's the same concepts as we move through and generalize from 1 dimension to 2 dimensions to 3 dimensions. Okay? Part of your last assignment, you're going to have your project. That'll be like 25 points. Part of your last assignment is to take the stuff we look at in Chapter 17 and go through and give it the limit treatment, continuity treatment, and all that other good stuff. All right? So kind of what we did here, generalizing as we go through. So once again, because the limit of a function of 3 variables is built on the same epsilonic architecture as the other limits we've talked about, all of the limit properties come over. So if we're trying to figure out the limit as x, y, z goes to 1, 2, 3 of the cosine of pi xz, we can mentally plug things in to see if we get a number. So the numerator would get close to the cosine of pi times x is going to 1, z is going to 2, over y, which is getting close to 2, times the natural log of x, which is getting close to 1, plus z squared, 3 squared. You get the cosine of 2 pi over 2 times 0. Oh, I'm sorry, 3 pi. Excuse me. This is a 3 here. Z is going to 3. Sorry about that. So this is the cosine of 3 pi, negative 1, over 2 times 0 plus 9. Boom, negative 1/9. So the substitution principle is alive and well with limits of functions of 3 variables. Similarly, all of the algebraic sorts of machinations you can do to try to resolve a 0 over 0 are going to be in play. The squeeze theorem would also be in play. Okay, so all that stuff comes over. What does it mean for a function of 3 variables to be continuous at a point? So once again, 1 dimension, what's it mean to be continuous? The limit as x approaches a of f of x is f of a. You get what you expect to get. We just talked about continuity here in 2 variables. you get what you expect to get. So what would be the difference here? All we would do is instead of having f of xy, we'd have f of xyz. Instead of xy approaching AB, we'd have xyz approaching ABC. And then you tell me, what should this equal if we're continuous? F of ABC. Make sense or not, folks? So there's your homework.